Fortunate enough to have our two remaining speakers here today. First, our third speaker at today's presentation will be Dr. Wesley Regian from the Armstrong Laboratory, and my apologies to you, sir, the Human Resources Directorate at Brooks Air Force Base, Texas. And Dr. Regian will be discussing he's a research psychologist and former teacher, and will be discussing future training technology, intelligent virtual training worlds.
Thank you. Great. Hi, my name's Wes Regian. I am the senior scientist of a group of psychologists, computer scientists, and artificial intelligence specialists. You probably wish I'd stand still, don't you? Tell you what, I'll confine myself to this area. That's the best I can do. There's two of you guys. What are you doing? Stereo TVs. I'm senior scientist of a group of psychologists, computer scientists, and artificial intelligence specialists at the Armstrong Laboratory here in San Antonio. We focus on advanced training technologies. Our customers include the Army, the Navy, the Air Force, NASA. Next week I'm going to Italy to address the European Space Agency. We build advanced training systems that are based on principles of psychology and instruction, and that use artificial intelligence and other important interface technologies. I'm going to keep this talk today. I know we have a very diverse audience, and I'm going to keep the talk primarily non-technical, but if anybody wants to talk nuts and bolts afterwards, that would be fine. I'm going to do kind of a survey. I'd like to start by providing a little bit of a historical context for what we do. We need to make a distinction between conceptualization of good ideas and implementation of those ideas. It's often pointed out that Leonardo da Vinci designed what was basically a workable helicopter. It would have worked if he had something more powerful than a few men to run the thing. He didn't have a sufficiently powerful engine. There was, in the artificial intelligence field, we point back historically to a Spanish inventor by the name of Quevedo in the early 1900s, who actually built a machine that played chess. Well, it didn't really play chess. It played an end game of chess. Well, it wouldn't play any end game of chess. It would play the end game where you've got a king and you're trying to defend against a king and a knight. He had the theory. He understood how to build smart machines, but he had to do it mechanically because it was prior to the digital revolution. If he had had digital computers, he had the theory and could have built a machine to play chess at that time. So both of these guys had good ideas, but they were somewhat before their time. The other technologies to support what they had to do weren't quite there yet. We are living at a time when some amazing stuff is happening, and I'm going to tell you about that amazing stuff, and you're going to see it emerge into the marketplace in the next 2 years. And boy, am I happy to be alive right now. Next slide. There was a fellow in the United States, a scientist by the name of Vannevar Bush. He's an American scientist. He did a lot of important early work that leads up to what we're doing today at the Armstrong Laboratory. He built analog computers at MIT in the 30s, for example. He directed the Office of R&D during World War II. Thus, he had oversight of over 6,000 scientists. He oversaw the Manhattan Project, which you may or may not think was a very nice thing to do, but it was a necessary thing to do at the time. He also oversaw the ENIAC project, which was an enormous early digital computer project that was funded by the DoD. Next slide. Vannevar Bush published an article in 1945 in Atlantic Monthly where he pointed out a couple of problems in science. He said that science depends on a record of knowledge. That is, the reason we're able to build technologies is that we don't always have to reinvent everything. I am able to work in the field of AI because people before me developed the appropriate languages and people before them built the right computers. Science builds on itself. Progress depends on the dissemination of knowledge. The problem that he pointed out was that the size of the knowledge record threatens our ability to make use of it. Sometimes, I kid you not, it's easier to do an experiment again than it is to find the reference to the guy who did it the first time. We have this enormous amount of data that we're trying to deal with. A good example of this is that Mendel's concept of genetics was very influential for a whole generation because the publication didn't reach very many people. It wasn't published in a journal that a lot of people were looking into. Next slide. In that same article, he pointed out that most systems of indexing are artificial and slow. He pointed out that the human mind does not work alphabetically or numerically, but rather by association. Now think about this. If you ever run across a person and you think, oh my goodness, I know that guy, but holy smoke, I don't know what his name is, what am I going to say? And a lot of times you think, you sort of sneak up on getting his name, you think, well, where the hell have I seen the guy? Ah, I saw him at the space conference. And then you slowly work your way into who he is. Your mind works well that way, by association. You associate the guy with the space conference. Finally, you remember, oh yeah, I saw his wife too, and she had a real big hairdo. What was his name? Ah, Ted Turner or something. So the human mind operates by association. Now this was a really important idea. At that time, he was like 20 years ahead of we psychologists who came up with the concept of semantic networks, which is not important to you, but it's the way we now understand how you think in terms of semantic networks and associations. What he referred to as the mind working in accordance with some intricate web of trails carried by the cells of the brain, we now call a semantic network. Next slide. He came up with the basic idea of hypertext. He invented hypertext. But again, he did not have the technology to do a good job of it. He proposed a thing called a memex, which is short for memory extension, which is a big device the size of a large desk that had in it a lot of mechanical linkages using dry photography and microfilm to store and display information so that you could link the fact that you met Ted Turner at the space conference and his wife had a large hairdo and he told you about several articles that were important. You can link all these things together. His device was theoretically doable, but very unwieldy. Sort of like early typewriters that were big and heavy, and the keys were always jamming. It would have worked, but it would have been heavy, would have been expensive. It never got built. What he described is basically a personal computer. Now we have a memex, it's called a personal computer, and we have hypertext, which is an easy way to move information around. Point being, oftentimes good ideas predate the capability to implement them. And I'm going to describe for you a couple of technologies that 5 years ago we couldn't do, 2 years ago we could do crudely. Today we're doing it at the laboratory, and it's the reason I work 12-hour days, and I'm perfectly happy about it because I can't hardly sleep at night for the excitement to get back to my office the next day and make this happen. It's amazing stuff. Next slide, please. Oh, gee, I've got to have myself. One of the groups that I work with is the Air Force Advanced Launch System group, and they have the Advanced Launch System Data Interface. It's basically Vannevar Bush's memex. It runs on a network of microcomputers, and it allows us to call up images of geographical areas and get definitions of words and just deal with linked information in a nice way. So, sorry, next slide. Now, I'm starting over. Whole new topic. Now I'm going to tell you about the technology that is sort of the focus of my talk. We have known for some years that private instruction is better than group instruction. That's why rich people hire tutors to teach their kids, because tutors can do a better job of instruction by teaching one person than a teacher can do in teaching 30 people. Well, why is that? There's a lot of reasons why that is. One of the reasons is that when you're teaching 30 people, if there's some joker in the back of the room asleep, you just kind of blow it off. What are you going to do? Like, you got 29 other people to worry about. Okay? When you teach to a group, you're forced to teach to the average student. You don't have the luxury of tailoring your instruction. The result of that is that if you compare private instruction to group instruction, the average student in private instruction outperforms 98% of the students in group instruction. It works a whole bunch better. No one can afford to do it. Next slide. However, we started about 10 years ago asking the question, well, maybe we can use computers to do private instruction. Now, 25 years ago, we started doing programmed instruction. But that was basically take a computer, put a bunch of pages of text on it, and let the person page through it at their own rate. That's not individualized instruction. That's self-paced instruction, and it's very different. It doesn't work very well. 10 years ago, we thought, maybe, since we've got these computers that work so well, and they're capable of indexing information so nicely and presenting graphics and presenting text, maybe, since we now have artificial intelligence languages, maybe we can make these computers teach in some way analogously. Analogously, is that a word? I've made it up. It's a word now. We can make computers teach like human beings teach in a private instructional situation. We call these things intelligent tutoring systems. We at the laboratory have been working on them for about 10 years now, and we have had a lot of successes. Intelligent tutoring systems have as sort of their base technology expert systems. Okay, an expert system is a computer program that goes through the same steps as a human expert in solving some problem. So we have expert systems that do medical diagnosis, and we have expert systems that do electronic troubleshooting. We've got expert systems that keep warehouses stocked. Things that human experts can do can be programmed. And an intelligent tutoring system uses two kinds of expert systems. One is a domain expert, the other is an instructional expert. If I want to build an ITS, an intelligent tutoring system, to teach you how to operate that camcorder, I start by creating an expert system in operation of camcorder. That's called the domain expert. It's a domain expert system. Then I go talk to someone who's taught lots of people to use camcorders, and I build another expert system that's called an instructional expert system. We've all run across a situation where we meet people who are really good at doing something but really bad at teaching it. And on the other hand, people that are mediocre at doing it but really good at teaching it. In this case, we want our computer to have two expert systems. One that's good at doing what it is you want to teach. Another that's good at teaching what it is you want to teach. We implement that in a computer. The result is called an intelligent tutoring system. There is a lot of multitasking happening in an ITS. We've got two expert systems running. We usually have some kind of simulation. A simulation of the camcorder, a simulation of a V8 engine, depending on what I'm trying to teach. If I'm trying to teach you orbital mechanics, I've got a simulation of physics. Okay? There's a student model happening. The system is maintaining information about the student. There's a lot of interface things happening. Most of my computers talk to you, so they have voice out. Because of all of the multitasking, 5 years ago I could do this, but I had to do it on a $50,000 special purpose artificial intelligence workstation. Today, I can do it on a PS2 Model 70, 8386 machine. The supporting technologies have caught up with us to the point where we can now build incredibly advanced intelligent tutoring systems that teach as well as private tutors. We have data to support that. It's still expensive to develop, but it's getting cheaper all the time as memory gets cheaper, as graphics gets better, et cetera, et cetera. Next slide. This is an intelligent tutoring system that I built 4 years ago that teaches orbital mechanics. It was delivered to Undergraduate Space Training School, Colorado, for the Air Force, and it was developed on a special purpose artificial intelligence workstation. At that time, this machine cost about $25,000. And it's not color, but it does have nice graphics support. Point is, I'm not talking pie in the sky. We really build these things. That's what one of them looks like. I have about 30 of them running in my laboratory, and that's an intelligent tutoring system. Next slide. More recently, I did some work with NASA. This is the propulsion console at Johnson Space Center. It is I hope there's no one in the audience that designed it. It is a human factors nightmare. It's very difficult to learn to use. It was built in the 60s, and in the 60s we didn't understand a lot about designing devices. It's hard to use. It's not designed well for people to use. we have developed an intelligent tutoring system to aid in the process of teaching people to use this device. Notice what it looks like. It's a big desk-sized thing with a couple of CRT screens and lots and lots and lots of buttons, switches, and knobs. Okay, next slide. This is the first screen of an intelligent tutoring system that teaches you how to use that thing. It says, "Welcome to the Intelligent Trainer for Mission Control Propulsion Console." This ITS was built in conjunction with my laboratory, the Armstrong Laboratory at Brooks, and Southwest Research Institute, SWRI, in San Antonio. Specifically, Dr. Pam Fink and Dr. Carol Luckhart, now Carol Redfield. What you see up here is a representation of that console, the propulsion console. Next slide. The system operates by focusing you in on pieces of it. Human beings, a good way to provide instruction is to break the problem up into smaller parts, teach the small parts, and then build it up into the large problem. Okay, and so what you can probably you can't see, but what we've done is highlighted this one keyboard, the manual select keyboard, enlarged it, put the large version down here, and we're teaching you how to use it. Okay, and eventually, once the system has successfully taught you what you can do with this part of the keyboard, it's actually demonstrating a procedure now. It says we will present an example exercise and work through it step by step. We'll demonstrate how to select display 7590, and it's actually pointing at a part of it, just like you would. If you were teaching someone to use a computer, you'd point at the escape key. It points at the right area, tells you about it, and demonstrates. This is an ITS that teaches propulsion console operation. It works well. We did an evaluation on it last year, and it teaches as well as a human being teaches. Next slide. One of the issues, I'm sort of changing gears again now, just a warning. One of the issues that we have in designing computers is making better interfaces. The earliest ITSs that we built were not well designed in terms of interface. That is, you would spend more time learning how to use the ITS than you would spend learning from the ITS. It's as if you had a teacher who's going to teach you mathematics, but that teacher spoke French. And so first you have to learn French, and then you can learn mathematics. Well, that's not a good situation, okay? And so the interface is just as important as any other aspect of a training system when we're talking about automated training systems. You want to design the interface to where it is straightforward and easy to operate with. As I mentioned earlier, we now have computers that talk to you. Okay, so that instead of printing stuff on the screen, they can say to you, "Welcome. Today I'm going to teach you," they don't sound as, I started to say as good as I am. I don't know how good I sound. They sound kind of tinny, a little metallic. But they're very understandable. They talk very well. And of course, we have computers that accept voice in. And those of us in the audience that are in that field know that voice in is not perfect yet. It's not speaker independent. We're working on that. My point here is that the interface barrier is an important one. We have to develop better and better interfaces so that we can interact with these computers in the same way as you interact with teachers. It would be a sad thing if I was trying to teach a class and I couldn't accept a question. If you couldn't stop me and say, "Hold it, I don't understand what you said. Unpack that business about semantic networks. What in the world is that?" Well, the bad thing about computers 5 years ago, computer-based training systems, is you couldn't stop them and say, "Explain to me what you mean." All they want to do is show you the next page of instruction. The interface is important. Next slide. We are developing a technology called virtual worlds. This is a little hard to explain. Oh, wait a minute. Anybody ever seen Star Trek: The Next Generation? You know what the holodeck is? We're building one. Okay? And here's how it works. It's not as good as the holodeck. Well, it's pretty good, though. It's not bad. Here's how it works. You go in a room, and we put it looks sort of like a diver's helmet on your head. And it's got two CRT screens, two computer screens. It puts one right in front of your left eye, one right in front of your right eye. And then we display an image on there, and the image is binocularly offset. Okay, the reason you see depth in the world is because you got these two eyeballs and they're seeing a slightly different perspective, and your brain is going, oh, that thing's far away and this thing is near, and that's depth perception. We simulate that. Okay? So we put one image on your left eye and one image on your right eye. We keep a little magnetic device sitting on top of your head, and it's a magnetic sending unit, and there's a couple of receivers hanging around the room, and we're keeping track of where your head is pointed. And if you turn your head, we update the graphics so that it appears that you're looking at a different place in this virtual world, this holodeck. And I've tried to, excuse my graphics here, it's the best I could do. I've tried to kind of crudely show that here. This guy, if he keeps his head pointing straight ahead, he sees the factory. If he turns his head to the left, the factory fades off to the right, and his house comes into view. If he turns and looks behind him, he sees the barn. If he looks to the right, he sees... Is that clear? You understand how that works? That's called a virtual world, virtual reality. Here's one reason that's useful in a training system. Suppose I'm trying to teach you how to operate the console of an F-16. When you sit in an F-16 fighter plane, there's stuff everywhere. It's amazing. There's buttons, switches, and knobs everywhere. I kid you not, everywhere. They're here, they're here, they're here. They're all around. There's no easy way to put on a computer screen to lay that out to allow you to see where all that stuff is. The way we do it now is we put part of it on the screen and we say, if you want to look left, hit the left cursor key 8 times and you go. It's very unreal, and you don't get the sense of how this thing is laid out. If we put a virtual world on set you up in a virtual world, we sit you down in a fake cockpit, you put the virtual reality on, you can see the front of what's in front of you. If you turn your head, you see what's beside you, etc. So now we have a way to have the computer show you exactly how this console is laid out. Another example. We teach people to do air intercept control and air traffic. Air traffic control is where people, they're trying to allow airplanes to land safely. Air intercept control is the evil twin of that. You're trying to get airplanes to shoot other airplanes down. In both cases, what you have to have people do is look at this radar screen and know that's not just blips floating around on the screen. There's airplanes in the sky, and that airplane is there, and this airplane is here. That's creating a large-scale spatial model from what you see on the screen. One way we're now doing that is with virtual reality. So we put you in the virtual gear. We have the radar screen here in front of you, and then you look up, and holy smoke, there's an airplane. See that? It's there. There's airplanes all around. Okay? So we're helping you create a large-scale spatial model using this virtual world interface. That's the virtual world. Next slide. Virtual interactive worlds. Anybody got kids with Nintendos? You seen a Power Glove? Power Glove is a licensed spin-off technology from a much more sophisticated thing called a data glove. The data glove, once you put yourself in a virtual world, put on these data gloves, and then suddenly you are physically present in the virtual world. You hold your hand out, and there's a cartoon representation of your hand. Okay? You can reach out and touch virtual light switches, you can turn virtual knobs, you can fly virtual airplanes. You now can affect the virtual world. It's sort of like a mouse lets you do things on a computer screen. We know what I mean by mouse, yeah. A virtual world, these data gloves let you do things in the virtual world. So that if I want to teach you a procedure of setting up the F-16 cockpit in a certain way, not only can you look around and see it, but you can flip switches, turn knobs, etc., etc. That's called a virtual interactive world. One of the really cool things about a virtual interactive world is this is just simply a computer database that you're moving around in. And so you have lots of power. I mean, you can design it any way you want. We've designed a world where it's basically an airport, and there's a tower, and inside the tower there's computers with blips on them, and there's airplanes flying around. And we allow the person to actually fly. And the way you fly in this virtual world is you take your data glove and you point where you want to go, and zoom, you fly. It's sort of like Superman, you know, except he has to go like this, you go like this. Right? And you control your rate of translation with your thumb. This is fast, that's intermediate, and that's slow. How many people fly in their dreams? Good, thank you for admitting it. Half the people in this room fly in their dreams. Me too. Others of you do and don't remember it. Okay? And there's a few that just won't admit it because it's just too childish. All right? Flying in a virtual world is a lot like flying in a dream. That will become important in just a moment. Next slide. There's a group at NASA. We aren't the only people in the world doing this. There are very few groups doing it because it's a very expensive technology to do. There's a group at Johnson Space Center, headed up by Bob Safely, that has developed an MMU trainer. The MMU is a manned maneuvering unit. It's the jetpack, the backpack that you fly around in space. And that MMU, you sit in a chair and it's got a joystick at each hand, and you put on the virtual headgear, and suddenly you see the shuttle in front of you. And if you turn around behind you, you see the space station, or what it might look like behind you. And using those joysticks, you can fly around through space, just like you were in the MMU. It's the most amazing illusion I've ever felt. It's as if you're there. It's a wonderful training device. We're using virtual worlds to train pilot flight skills, so that we put you in simulators, have you flying around. You can look left and look out the window and see the bad guy coming at you to shoot you down, etc. Remote manipulated RMS training. That's the robot arm on the shuttle. That's another potential use for virtual world training. Onboard skill maintenance training. One of the issues that NASA is thinking about as they go with longer and longer shuttle missions is the problem of skill degradation. Landing the shuttle, that you've all heard, is like landing a big brick. And you have to be skilled to do it. The longer you're up there, the more your skill degrades. Skill degradation is a fact of life. We can use virtual worlds to provide simulated training for landing while you're in the air. Now, I'm real excited about this issue, onboard therapeutic recreation. We learned in World War II that some people cannot be in submarines for very long before they get really hard to get along with. Really hard to get along with. Okay? Maybe. But part of the problem is claustrophobia. I mean, they're in this like little thing, and they're in there for a long time, and they're in with the same people, and it's a bummer. Maybe if you put people in a virtual world once a day and let them fly around in a jungle, they can take these long space flights that we're now starting to contemplate. Okay. The other thing is remotely actuated robots. I can put on a virtual suit and drive a robot, where when I move my hand, the robot's hand moves. And when I turn my head, the robot's head turns, and I see what the... I know her. When I turn my head, the robot's head turns, and as a result, you can do things from far away. For example, you can't take surgeons with you, well maybe you can, but you can't take every kind of skill you want with you on a long spaceship, and it's possible to use virtual hookups so that you can have a person on the ground conducting an operation on the moon, for example. Okay, I'll stop. So, I didn't have any more slides. Oh yeah, I want to say one more thing. Intelligent tutoring systems are here and now. Virtual worlds are here and now, but my setup requires 2 Silicon Graphics Iris 4Ds, pretty high-end Silicon Graphics computers, 1 Mac FX, a set of iPhones that cost $35,000, 2 data gloves that cost $8,000 a pair, some analog to digital converter boxes, a bunch of software. It's about $300,000 to get into this business. 2 years from now, it will be $100,000, and 2 years after that, you'll be able to do it on your home computer. I promise. Thank you very much.
Our last speaker today will be Ms. Shirley Ratcliff from Southwest Research Institute here in San Antonio, Texas. and she'll present a demonstration of digital multimedia, a training tool to counter space-age information overload.
Actually, can you all hear me okay from the back? If I don't go up there. I've worked with NASA JSC on several training needs assessment studies, both with the Space Station Training Office and also for the Flight Data Systems Shuttle Software Branch, doing training needs assessment for their employees. He introduced me as doing a demonstration. Actually, I don't have it in my computer equipment here, so it's not really a demonstration, but I'm pretty interactive, and as you learned from the previous speaker, I'm going to be able to shortcut a little bit of my talk, partly based on some of the things that he said. Primarily, I'm going to go over just touch on the concept of multimedia, and I think he did a good job of that, and talk about why interactive multimedia is particularly relevant to this information age. Focus a little bit on some of what gives substance to some of the technological wizardry that we have, and in doing so illustrate some examples of training applications that are good candidates for this type of technology. First of all, in case you think it's a that helps. Winsor McCay was a cartoonist in the early 1900s, and he did a vaudeville act that involved interacting with this animated dinosaur that was on the screen behind him. The audience actually loved it and was really fascinated with it. He would talk to it, throw food to it, scold it, make it cry, and so forth, and then as a finale, what he would actually do during the act is he would walk toward the screen as Gertie lowered her head, and then he would disappear in a slit in the screen, and then the animated Gertie would lift an animated Winsor McCay up for the end of the act. Actually, contemporary audiences are pretty charmed by watching footage of this act. The previous speaker, excuse me, so I don't talked about interactive training, and I just wanted to point out that just not to limit it to just what you can see on a two-dimensional screen. And I'm going to concentrate a little bit more on full motion video, especially in view of the things that he discussed. In our training needs assessment at NASA, one of the common threads that we encountered once we ruled out some of the things that could be addressed with non-training means was this huge information problem. Not only are there large amounts of information that, say, the shuttle software analysts needed to get to, but the information that they had was frequently tightly coupled with a lot of peripheral information in other functional areas of the software that they were in charge of. And if you're familiar with NASA's talent for creating reams and reams of documentation, many times the new software analysts would come in and be handed a stack of documents like this and say, well, here's your little world. That's also complicated by large variety of resources for information. You have different data sets you might get information from, the documents. You don't know whether you need to go interview a contractor, interview a coworker, and I think you're very familiar with the different sources of how various sources of information can complicate figuring out exactly what you need to do to perform your job. Other complicating factors besides just this huge amount of information are the time-critical schedules that the space program runs on, and especially in the shuttle software group, they're mission-to-mission oriented, and so they have schedules that they have to meet and get all this information integrated. And with a new analyst, it took a long time for them to really get to know their functional area of the software and also figure out the system, how to get the code changes through the system. Some of, I'll use the shuttle software analyst as an example of the different approaches that they had taken to get their new people over that learning curve. They, of course, did on-the-job training, which involved having one-on-one teacher take them through managing the software code. They also had contractors come in and give stand-up lectures and teach about the various functional areas of software, and also co-workers, the NASA analysts, doing the same thing. They've also worked with doing some computer-based training, but primarily the computer-based training that they've been doing prototypes with just use text and graphics. Well, whenever we were doing our interviewing of the analyst, you sit down and you talk to them, well, what are the types of things that you do? And frequently they'll have a tendency to start talking about the technical aspects of the code. Just these reams and reams of information. Well, as it turns out, when you really say, no, but what do you really do? Frequently, they go to a lot of meetings because they're managers, they manage the code, and they end up doing an incredible amount of interacting and communicating. Of course, they have the technical knowledge as a background, and as they become more adept in their functional area, they have to know their functional area very, very well. But a lot of their day-to-day activities involves a lot of other things other than just knowledge of the software. And one of the complaints that they had about the traditional types of training that they were doing is the analysts would come in and get videotapes and go to these lectures and get this documentation. Their main complaint was, well, this is really boring. So one of the things that we look at when we do training needs assessment, especially in a sophisticated audience that is highly motivated, is that your training also has to be fairly, well, it has to be sophisticated enough to where they have enough user control. Otherwise, they're going to get bored with it and they're just going to go along on their own and learn on the job. I'd like to just go ahead and point out some of these training system variables that help a training system be successful, and why multimedia is particularly valuable for these variables. The attention is one thing. If you don't get your trainees' attention, they're not going to do it unless, of course, you force them to. And the other thing is the relevance. If many of the traditional lectures that they had gone to are similar to how you would teach in school, you just teach from a knowledge base. You talk about this area of the software, you talk about this area of the software, you talk about this area of the software. Well, one thing that we really try and do when we're using digital video or interactive video is to be very performance-based and come at it from the perspective of the student instead of just teaching large amounts of information. Really concentrate on what types of things they need to know to get their job done. And in this case, it was manage the software code. So if you can teach from the perspective of the process that it takes to take a code change, go through all the different board meetings and give them an overview of what it's like on their job, then you can go ahead and nest down further and further however much money you have to spend or however much need you have to get more down to the technical detail. One of the things that this does for a new analyst is that it can bring them in and immediately increase their confidence because they can see the big picture idea. And then when they go through the actual process, they already know, the 6 to 8 week process that it takes to go through that, and they're much more adept the first time through when they actually start their on-the-job training. The satisfaction levels when you take your training and put it from the perspective of what they're actually doing goes way up because they have a much better idea from the very beginning about what their actual job is going to be. And with multimedia, and in particular, when you can mix text, graphics, pictures together, you can mix and match both the technical domain and the affective domain and really concentrate on the training need. One of the things that I'd like to point out that you really need to have to be successful in creating multimedia applications is, number one, a training need. And that may sound very simple, but it's something that a lot of people really overlook, especially if they get involved with technology. They go around with a hammer looking for a nail. The other thing is a supportive development environment, and that's really critical in this technological area, because if you're going to be mixing graphics and doing production work, you need the people and the tools to integrate all of those, and also the authoring system, so it's more cost effective. NASA is a good candidate for some of those things, especially if you're getting up at a higher level overview, because they do have a lot of public relations, video and film and graphics already there, and also the production capabilities. So we've been able to do several interactive video applications at a much lower cost than what it would take to take an industrial client and do the same thing for them. And the last thing that is really important is this emphasis on content. I know the previous speaker talked about having your subject matter expert and your instructional expert. Too many people get too involved in creating applications without really giving it the substance and taking it from the performance spaces I spoke of before. One of our recommendations for the shuttle software branch was to take their approach differently, mix the affective domain and the technical domain, and instead of trying to take all the 100 areas or whatever of software and extract all the information about that particular software and putting it in a computer-based training program, they could go ahead and maybe take one of the process. For example, how an analyst maps the functional requirements of the code to the actual code, and teach that process, which is a process that most people go through when they're learning about a particular functional area. And also intertwine that with actual video footage of perhaps board meetings and so forth, for them to get a feel of what's appropriate, how they should interact with people. At their level, they worked with people that are above them, co-workers, below them in the sense of being contractors as opposed to NASA employees. And concentrate on the process simulation, at least initially, and then if you have the time and you think the shuttle will still be around by the time you get done with all of those different areas, then you can go ahead and fill in the spaces, use your artificial intelligence to do intelligent tutoring and things of that sort. Another application that I was going to talk about a little bit that we have done at the Institute is an equipment simulation, and it is also particularly well suited to interactive video. It also relates fairly well to some of the things that on the space station side of the house that we were looking at. This is a robot that strips paint off of aircraft, and in particular it's a very expensive, just like many of the simulators at NASA, and they didn't want to have downtime for the robot for someone to actually learn how to operate it. And so what we've done is an interactive video program that, one, teaches them about the overall concepts of the robot and the computer interface, and then actually hooks the handheld interface device up to the serial port of the computer, and the person can actually get on there and practice the different steps, the sequential steps that it takes to operate the robot, and what they see on the screen, if they do the sequence of steps to say move one of the axes up, they see that axis move up, and then they can change and go down and see the axes move down. It's a very effective way to introduce them to some of the mechanics too, and the procedures that they go through to actually operate this robot without having to have downtime on the actual system. And mainly, I guess, to summarize here, I'd just like to emphasize that in order to do multimedia training, which can have a lot of other advantages in addition to the training, you can do presentations and you can do a lot of other training that's related to the type of training that you do. But the important thing is to really emphasize the content and make sure that what you have there is substance as opposed to just technological wizardry.
Thank you.
Thank you.